PES is also a very valuable tool to look at when we're seeing results or we're seeing patterns that we don't expect. So nitrogen and oxygen are in the same row on the periodic table. And we've seen that as we add more protons, we tend to have greater attraction for electrons, and that greater attraction corresponds to higher ionization energies. When we look at nitrogen compared to oxygen, right there, 52 compared to 39, a higher value, harder to remove. 3 compared to 2.4, harder to remove. But the last or valence electrons are 1.3 compared to 1.4. So in terms of my sloppy handwriting here, both of those go into the 2p sublevel. And as they fill, nitrogen has one electron here, one electron here, one electron there. It equally spaces those out following all of the rules, Pauli, Hund, and Aufbau. Oxygen also follows the rules, but it has to double up within an orbital. What we see, and one of the rules, we referred to this before, and it's coming back, is that we want as few electron-electron repulsions as are possible in the configuration. Oxygen has more protons, so it pulls its electrons in more tightly, but that second electron within that orbital repels the electron that it has to share that orbital with. So this electron, the last one I drew, is actually somewhat unusually easy to remove from our atom. So when we connect PES with ionization energy data and then back to electron configurations and orbital diagrams, we can get a full look at why an atom has the property that it does. And that's a very common way that you would see something like this asked on the multiple choice in the AP exam. Why is this peak bigger than this one for oxygen, but why is this peak smaller than that one? So acknowledging the general pattern of more protons, but also recognizing when an exception exists and trying to find the cause for that.